Good morning, students. It's Friday, March 27th, 2020. Welcome to Earth Science. Today's lesson, I want you to be able to explain how convection within our Earth causes plate tectonics. I can name the different types of plate boundaries, and I can list physical features of the Earth that occur at those boundaries. So I want to take care of a couple little details before getting into the basics of plate boundaries. I want to talk a bit about the difference between continental crust and ocean crust. So here's a diagram. This is showing what's supposed to be a continent. We see some mountains and some thicker. And here's the ocean, and under the ocean, of course, we've got a surface. There's a solid surface down there, too. Now, there are some differences. Continental crust tends to be thicker. It tends to be less dense. And I should say that continental crust tends to be more felsic in the nature of the rocks. So there's more silica. It's the lighter earth. It's as far as rock goes, it's the light and fluffy rocks. Okay? If someone's going to hit you in the head with a rock, you want a felsic rock. Okay? Lighter, fluffier. Don't do that. Don't try that at home. All right. And because it's lighter and fluffier for rock, it tends to float a little higher on the mantle because the mantle, remember, is ultramafic. Okay? Ocean crust tends to be a lot thinner. It's more dense. So it tends to sit a little bit lower on the mantle. Now you see that our continental crust here extends lower into the mantle, but think about it, that's because you got all this extra weight. Even though it's fluffy, if you put enough fluffy stuff on top, it's still heavy and it's pushing down. So we get this thick layer of crust. It says that the continental crust sometimes can be up to 70 kilometers thick. Ocean crust is often just 6 to 10 kilometers. So 10 kilometers is a little over 6 miles. That's not very thick, okay? That's the surface of the Earth underneath the oceans, okay? The ocean crust tends to be mafic in its nature, and then the mantle that's underneath, remember, is ultramafic. So felsic has a lot of silica, mafic not so much, ultramafic is really low in silica. Okay, the more silica, the less dense it is. Okay, just a couple of terms. Magma and lava. Okay, both of those refer to molten rock, molten or liquid rock. So what's the difference? Why do we have two terms? I don't know why we have two terms, but the difference is if it's below the surface of the Earth, so here's my picture trying to represent the surface of the Earth. If it's below the surface of the Earth, it's called magma. And if it's above the surface of the Earth, it's called lava. So I say molten rock. Lava is molten rock that has flowed out onto the Earth's surface. I have to point that out because I'm very proud of how my words flow off the edge there. Okay, another basic thing. We're going to talk about some energy transfer. We have conduction and convection. Convection is going to be particularly important in what we're about to talk about, but both of these things happen in Earth. So conduction, if you have solids, the primary method for heat to move is by conduction. And it says it's energy transfer by contact from particle to particle, like dominoes. So imagine this. I've got a molecule that's got some energy, and if it's got a lot of energy, it's moving fast and it bumps into the next molecule. Well, when it bumps into the next molecule, that molecule gets some of that energy. And it might bump into the next molecule, and the next, and the next, and the next. Like dominoes falling. One has energy. The energy travels down the line of dominoes, and yet the dominoes just, they move a little bit within their place, but the dominoes don't go flying across the room. The energy travels. That's conduction. So if the core of the Earth is really super hot, those atoms are moving fast and they're bumping into the next atoms above them in the mantle, the mantle that's touching the core, and the heat is traveling by conduction some. Now we get to convection. Convection is the primary method of heat transfer in liquids and gases. And the idea is that liquids and gases are able to move. Solids, the particles are moving back and forth, but they can't go anywhere. In liquids and gases, the particles can actually move and flow. And so what happens is convection is the energy transfer by bulk movement. Okay? Now, bulk just means a lot. Okay? The matter is actually moving. Bulk movement of matter. So a portion of the matter actually moves and takes some of the energy with it. So imagine I've got a flame. The matter right here gets hot because, well, it's in contact with the flame. Okay, that's conduction. But now when this matter gets hot, those particles are moving faster and faster, and they bump into each other harder and harder, and they spread apart from each other. And I think we've done that demonstration in class where I've had a couple of students up here. Okay, so if those particles are spreading apart from each other, then what happens is that matter becomes less dense and tends to rise. And so the cooler matter over here tends to flow. And so we actually have the matter itself is moving in convection currents. I know we talked about convection currents in the sun. We're talking about the same thing here. Alright, so here's a slice through the Earth just showing our crust, mantle, and core. Now, the core, we've got a solid inner core, we've got a liquid outer core, and the mantle is made up of rock. But it's rock that's under really high pressure, and it's rock that's at really high temperature. And so at geological speeds, that rock actually flows like a liquid, like a fluid. I say geologic speed. I mean, we're maybe talking that it flows, I don't know, an inch a year, something like that. That's not very fast. So from our perspective, it's solid rock, but it is moving. And so we have places where the mantle is rising. We have other places where the mantle is sinking. We have these convection cells within our mantle. Now, this is trying to zoom in on one of those cells. This is where I had mantle material rising, and as it gets to the surface, it's got to move away. And over here we've got the sinking cell, and here we've got the sinking cell. But if you consider what's happening right at the surface here, basically your mantle motion is sideways, that way. And over here, your mantle motion is sideways, that way. And think about what that's doing on that brittle surface of the Earth. We've got the mantle is trying to pull in two different directions, and so the Earth might crack open. This is called a divergent plate boundary. What we have is two pieces of the Earth are being pulled in different directions. Divergent means to pull apart, to split apart. Okay? That is, important vocabulary for us. So we have convection currents in the mantle pull on sections of the crust. In some locations, pieces of crust are moving away from each other. They're diverging. And one thing that can happen is we have this crack in here. If we have a crack open and you have this valley in the Earth, that's called a rift. Another vocabulary term. Now the next slide maybe doesn't seem related, but I thought this is maybe one of the best places for me to put this. Here's a diagram of Earth, and all those yellow, orange, and red dots on that diagram represents where earthquakes took place. And this data was from 1990 to 2005. So we've got 15 years worth of earthquake data. The yellow dots are the smallest earthquakes. The orange dots are bigger-ish, and the red dots are monster earthquakes. And when you look at this map, does it not look like the Earth is broken into pieces? Okay? Right here is what we call the North American plate. Over here is what we call the Eurasian plate. Here's what we call the African plate. Here's the South American plate. Here's the Pacific plate. Here's, I think this one's called the Nazca plate. The African plate is in the process of cracking. And so you've got, I forget the names. Instead of African plate, I think one is the Namibian plate. Sorry, don't remember the names. But it's cracking open along here. And so this part of Africa is actually splitting off of the rest of Africa. Anyway, the purpose of this was just to show you these sections of the earth. So I've used the word plate a few times. This whole concept is called plate tectonics. And what it's saying is that the lithosphere of the earth, the surface of the earth, is broken up into pieces. And you saw the pieces kind of defined by those earthquake lines. Those pieces are essentially floating on the mantle, and they move around due to the convection currents. Okay, plate tectonics. So I'm going back to our first type of boundary that we're going to look at is this divergent plate boundary. So I already showed this where the mantle is pulling apart here, and so the plates on top are being pulled apart, and we can get this crack in here. And I showed you a rift valley forming in there. Well, you know, if the crack opens far enough, that releases the pressure down below, and some of that rock, when it's under less pressure, is allowed to melt, form magma, and the magma builds up pressure and might push out. Now we got lava, we got volcanoes. This is one of the places where we get lots of volcanic action, is at divergent boundaries. Yeah, all my text I think says what I just said. Okay. So, what if this divergent boundary was in the middle of an ocean? Well, then this ridge of volcanoes here, that's the mid-ocean ridge that we talked about, was discovered back in World War II. Mid-ocean ridges occur where two pieces of oceanic crust are diverging, and the magma rises in between to fill the gap. And the magma is hot, so that rock is less dense and builds up higher. Here's more of a close-up of the divergent boundary. So you imagine here's a piece of plate moving that way, here's a piece of plate moving that way. It cracks open in here, pressure is reduced, and when the pressure is reduced, that allows magma to form. Because remember, the earth down here is generally solid rock, but conditions can happen like reducing the pressure where magma is allowed to form, and that magma may push up. If it isn't filled with magma yet, we may have a valley in here. It's called a rift valley. Magma pushing out and creating that ridge. If it's in the ocean, we call it a mid-ocean ridge. So I said I want you familiar with the different boundaries. I also want you familiar with what features. So what are some features we could find at a divergent boundary? We could find rift valleys. We could find mid-ocean ridges. Right here is a picture of a rift valley on land. And you can see there's a crack in the land. These pieces are moving apart from each other at geologic time frames. We're talking an inch or so, maybe a year. And that crack is forming and fills in. Now, there's very likely along this rift, there's places where there may be volcanoes forming, because as you reduce that pressure down below, you get magma and volcanoes. Okay, so what if we're looking at a place where, see how this is my convection cell where now the convection is sinking, and so this part is pushing this way and this part's pushing this way. So the lithosphere that's riding on top of the mantle is being smushed together. Okay, smushed together is called convergent. So some pieces of the crust are moving towards each other. That's called a convergent boundary. Now, convergent boundary is what we're going to find there is going to depend a lot on what type of crust we see. So I'm going to start out with the case of two pieces of continental crust. And you remember from earlier, we said the continental crust is mostly felsic in nature. It's the lighter, fluffier rock. It's not as dense. And so neither piece wants to sink. And what happens when these two pieces come together is they smash together and they buckle and fold and bulge upward. That's going to create a mountain range. The biggest mountain range in the world, the highest mountains in the world, are in the Himalayas. And the Himalayas is where the Indian subcontinent is smashing into Asia, and it's buckling. And we get really tall, high mountains. What if you have a piece of continental crust and you have a piece of ocean crust? Well, now this is much less dense. This is more dense. And so what tends to happen is the more dense piece actually bends and pushes underneath the less dense piece. And that's called subduction. Subduction is when the one piece moves under. And a couple things happen because of that. You can see that this front edge, it may get piled up some. Certainly, we may get mountains in here. But as this piece is dragged down into the mantle, it drags along with it some water and some sediment. And that combination of water and sediment with the rock, it changes the melting point of the rock underneath. And it makes it easier for some of this material to melt for magma. And if you have magma, it's going to look for a crack to try to force its way up, and we get volcanoes. Now I want you to think about this. The volcanoes aren't happening right here at the end of the continent. They're happening some distance away from the edge of the continent. I don't know, 50 miles, 100 miles, 150 miles, but somewhere in, because that's where this magma is rising. What we have right here is a trench. Remember, we saw that there were places along the ocean where there were deep trenches. So where this plate is being pushed down, we get some of the deepest parts of the ocean. So with convergent boundaries here, we can have a volcano arc that happens. We can have mountains from it buckling a little bit. We can have a subduction zone. We can have deep sea trenches. Those are all features that form. What if you have two pieces of ocean crust? Okay, that happens. So two pieces of ocean crust, when they come together, well, one of them is going to be more dense than the other. That's just the way it is. And it's typically the older piece is more dense because it's had a longer time to cool since it was magma. And as it cools, the rock gets more and more dense. So the older piece of crust is likely going to get pushed under, and really we can just repeat everything else that we had on the last slide. We get a subduction zone, we can get an arc of volcanoes, we can get a deep sea trench. I think the Marianas Trench, the deepest part of the ocean, I think is this type. It's certainly a subduction zone. I can't say for sure that it's two ocean crusts. It might be an ocean and a continent. I think it was two ocean crusts there. Okay. So one more possibility. We had where they were spreading apart from each other. We had where they were moving towards each other, either buckling or getting a subduction. What if they're mostly just moving side by side? That's called a transform boundary. We got two pieces of crust, and they're just kind of moving side by side, parallel to each other. Okay? They're not really moving apart from each other. They're not moving together. They're moving parallel. What tends to happen here is they tend to build up. They don't move smoothly and evenly. The pieces, they have, they're not smooth pieces of rock. So they have little notches and bumps and everything, and they're stuck together. and then they build up pressure and all of a sudden let go and slide. And when they slide, you get a lot of shaking and movement. So these zones are really known for earthquake action. If you get a lot of earthquakes without the volcanic action, there's a pretty reasonable chance that that's a transform boundary. Now, think about a convergent boundary where those pieces are sliding together, buckling. You're going to get a lot of earthquakes there too. But oftentimes you're going to get, well, I guess the difference is this one's not really going to be forming the big mountains. It's not going to be associated with volcanoes. So if you have earthquakes but not really associated with mountains and volcanoes, that's a good idea of transform boundary. Where does this happen? Oops. I thought I had a note on here. Okay. You hopefully have all heard of the San Andreas Fault in California. The San Andreas Fault goes up much of the length of California. It's a crack in the earth. And basically, in California, if you think about the part that's on the coast and the part that's further towards the continent, the part that's on the coast is moving north-northwest at a faster rate than the rest of the continent. And so we get sometimes some really terrible earthquakes along there. I watched just a week or so ago a movie with Dwayne Johnson, The Rock, called San Andreas. Not at all a accurate representation of earthquakes, but if you're just looking for some entertainment and, you know, okay, it's at least got earthquakes in it, maybe you want to check it out. So, that's basically it. So today you were looking for water plate tectonics. What are the different boundaries? We had a divergent boundary, convergent boundary, a transform boundary. What types of features happen? At a divergent boundary, we had rift valleys, mid-ocean ridges, volcanic action. At a convergent boundary, we could have, you know, huge mountain ranges if it's two continental crusts coming together. We can have subduction zones, deep sea trench. We get volcano arcs. Definitely going to be some earthquake action with that. And then the transform boundary, more known for earthquakes without some of those other features of mountains and volcanoes and things like that. Although some of the world's devastating earthquakes are associated with those transform boundaries. So, yeah, that went a little bit longer than I thought it was, but that's all right. We'll get over it. Next week we're going to get into doing some practice on this material. So have a great weekend. Take care of yourselves. Stay safe.